Let's continue, and second time we obtained a blocking layer. Now is a modified or systems is an applied a blocking layer. Blocking layer applied after applied is some leakage of the electrodes or some leakage of the electrolytes blocking by the blocking layer, and it means that it is reduced to the rejunctions and the short connections, and it's increase the efficiency of the solar cell. Therefore, we want to apply a blocking layer. Let's continue with blocking layer, sorry. Yep. It is so thick layer to coat this thick layer to TCO. As you can see, FTO layer or TCO layer we produced before, and we applied the blocking layer to enable to leakage of the some electrons lost and the photovoltaic electron lost, and we can more efficiency we can apply. As you can see that our blocking layers so thick, it is so thicker than the FTO layers also. If you compare 300 nanometers near the less than them, but it is still highly reflected, and it's highly transparent. It occurs also, and this is after applied increase the efficiencies increase slightly also, and this is again showing the best performance on the quantum efficiency, but it is still not enough. Then we applied some layers to like a grape layers to catch the like a created arms to catch the whole of the titanium dioxide layers by the grape-like seeded systems. Then after applied the systems by the solar sol-gel again, as you can see the systems, and we applied we base systems after applied this grape-like systems, we can nanowire systems, we get it highly photocurrent efficiency and the highly quantum efficiency we see, and also internal resistance means that resistance of the curves is decreases. It gets highly decreases of this resistance. It means that the whole of the electrons of the photocurrent electrons means that created by the N junction after PN junction related to produce the photoelectrons to easily to follow to reach the ITO level or FTO level is too easily, and it increases the efficiency. Therefore, electron movement if increases, but still not enough. After produce FTO, and we applied some grape-like systems here, and we produced in the first structures of the titanium dioxide here, but still some light is incomes, but it is so transparent. Therefore, whole of the if you send it to some lights, nearly we lost to 50% lights. If you doesn't use the scattering layer, you lost. Means that the efficiency, if we want the efficiency increases, we have to scattering the light after the applied photo induced current here, and no wavelength light it can be escaping due to the scattering layer, because scattering layers stopped off to them and back to the absorber layer. Again, the photocurrent efficiency increases here, means that some photocurrent electrons produce here, and you can get it more electrons. Again, if it's a theory is like that, and we applied some scattering layer in there. We choose that zirconium oxide scattering layer due to the look at some structure of the literature, and we obtained zirconium biggest particles of that, and we get it highly efficient value and the highly efficient solar cell obtained finally. How is that? let's final structure. We will compare that in our systems. Actually, we start from here. If you remember that in the first slides, and we can obtain the like there. Now is the efficiency, the 7%, 5. It's close to the literature value. Literature value sum of efficiency is higher than them. For example, 20%, but it is just a 1 centimeter square systems. But in this systems, close to 10 centimeter and 10 centimeter. If you applied this systems is an not a scientific value, you want to produce a panel, you have the biggest size of the efficiency is important. For example, silicon cells is showing the 25% efficiency in again 1 centimeters squares. But if you a panel efficiency is less than that, close to the 80 or less than the 60. It means that it's lost that a lot of energy by the making some panels to make a silicon cell. But in the structure, it's not a loss like that. We obtained 10 centimeter, and or 1 centimeter square sample is the same value we can get. Nearly 7.57 efficiency we can get in the 1 centimeter square samples. Therefore, this kind of systems can be used as some military applications. I will show that into you. Then yes, here, and these systems now usage in the or army structures can be flexible. It's my hand, and you can see that. Let me show. Yes, it is flexible. As you can see that it's not a decomposable. Also, any bullet is taking in the systems, and the other systems still working. That means that this, if you this working is system continues working like that. But silicon, however, silicons, if any bullet is target of the or hit it to the whole of the silicon system is not usage. Therefore, it is not suitable for the defense industries or defense applications. And this system directly usage on defense systems. And there, as you can see that. And also, this is NATO projects, NATO, but it's scenic, but some Turkish value. Sorry, my fault. This is NTO sets 280 projects. It's still going on, and I manage that. And also, I'm working some the teammates which we can collaborate with you also, because Pakistan and Turkey is a so kind, so friendship countries. Always with, and also we work with the some camouflage systems by the thermal cameras, as you can see in the picture. Also, we can modify some infrared blocking layer by the usage of some titanium dioxide and some organic molecules together, and you can see that whole of the tanks as a car, or you couldn't see tank on the infrared cameras. Why it's so important? Because whole of the missile systems in the infrared missile systems, or just the connections of the infrared lights and the heat of the engine of the some cars and tanks and some systems on the. Therefore, we have to protect our car defense or the tanks and some systems, and also some flight and the helicopters. All of them they coated by these materials, and this is the NATO productions materials, and this is the also Turkish laboratories produce. Is by hand. It's my hand also. It's compared that, as you can see that Turkish system is the very good. Sorry, it is OR systems, it's NATO systems, but NTO systems still well, but not good. And you need to more consume also the chemistry and the chemicals. But however, we just little bit chemical we use applied. This type of this stick to say some things, but I can say the some things to you. It's just a compare some graphenes and the titanium dioxide and some organic molecules composed together we applied. Actually, self-cleaning materials, again, they illustrated with energy systems. This is the coated some textiles, and it is can be clean itself by the sun, use the sunlight. Again, the director systems is work like that. Is a like a dye-centered solar cell on a potaton, but just self-cleaning systems, not produce electrons, just cleans the
Assalamu alaikum. Well, my name is Dr. Tayyib Qureshi, and I'm working in University of Lahore, like since last 7 years. And for all this, like opportunity that Dr. Muhammad Farooq has provided me, I'm very thankful that I'm standing here right now in front of you because he's my supervisor as well as he's also a very prestigious part of this conference. And in addition, I would like to thank Mr. Dr. Jamshed for all the invitation and the correspondence he has done in order to facilitate regarding this presentation. Assalamu alaikum. Well, today let's start with the presentation. It's some part of my PhD research work that is based on the fuel enhancement of biomass. So we have experimental analysis for developing organic waste biorefinery model in Pakistan to achieve sustainable development goals. So this we have the presentation content, in this we have research background, motivation of the research, materials and methods, experimental results and discussion, conclusions, future recommendation and references. So the research background behind the research, all the narrative is actually that we have to achieve the zero emissions in order to attain the sustainability. Well, there are many different ways as it is mentioned in Sustainable Development Goals, like we have 16 to 17 SDGs, and in that regard, in that picture, I'm targeting the goal that is clean and affordable energy. And for that purpose, what I'm trying to do, I'm trying to improve the fuel quality. I'm trying to add the value to the fuel as well as to the component that is related to the fuel in order to integrate with the bigger vision concept that is a biorefinery model. Now, what is the motivation of the research? The motivation of research is that that's a quite crucial thing that we have to adopt this more waste to energy concept in our country, because we do not have any such kind of grounds available. We do not have any such kind of working that is practically available that can be integrated in the society. For that purpose, what we need to do the awareness. We need to address in a mechanized approach. We don't need to think like if there is something happening around us, how we can achieve it. So all these conference sessions and all this like awareness of waste management companies, right now we are in the awareness phase. Actually, we are getting the energy out of many sources. There is a potential, but still we have to realize the importance. So what we have to realize that there is nothing waste in this world. Everything has its importance. What we have to do, we have to integrate the waste with the technology and we can have wonders out of it. Either it's a solid waste, either it's a liquid waste, either it can be semi-solid waste, whatsoever kind of waste it is. So it can all be covered, it can all be improved in terms of fuel, in terms of product under the bigger umbrella of biorefinery concept. So what I have done, I have taken, there are a lot of biomass samples. We have a cotton stalk, we have wheat straw, we have rice hulls. But why we have taken the cotton stalk? Because all the waste that is being produced from the cotton stalk has a good potential in terms of energy production. So in a bigger picture, biomass conversion unit, biomass converted into form of energy, and along with that we integrated this component with a biorefinery. So what actually biorefinery is doing? Biorefinery is analyzing that what kind of waste, so that what kind of technology that can be incorporated for the purpose of biomass conversion. Okay. So this is actually the formation of flow chart, the sample formation. In this we have taken the raw sample, then we have washed it. After that we have done the drying procedure, and then sieving of the sample was done, and after that we have done the demineralization of the sample and put it on the orbital shaker for the thermomechanical treatment, and after that filtration was done, leading towards dehumidification and a neutralized dry sample. And the neutralization of the sample was witnessed with the help of litmus paper test. Well, this is actually the depth about the circling mechanism that we have chosen 250 RPM rotation cycle in order to produce optimized interaction between the leaching agent and the biomass sample. So, this is the graphical abstract of the research work. There are notions that we are trying to achieve SDG 7, SDG climate change, and SDG sustainable consumption and production. And along with that, there are two ways we are trying to achieve it. We are trying to do the thermal characterization and structural characterizations in order to facilitate, in order to justify our studies for the practical applications. Well, this is a scheme which we have adopted. As I mentioned earlier, that we have produced the sample, biomass, sand to shred formation, and then we have biomass powder form, thermomechanical treatment, neutralization of the sample, and then treatment was done in order to achieve different formations. Like we have 5 samples, 5 working sets that is being produced on the basis of variation in the demineralization time. And then what we have done the thermal evaluation. We have done TG analysis, DTG, DSC. They all belong to a similar set of nature. They are actually thermal base analysis and gross calorific value, carbon hydrogen analysis, reactivity, and kinetic analysis. Well, this is thermogravimetric analysis. Thermogravimetric analysis presents the mass loss of the sample against the temperature. And what we have concluded that with the increase in temperature, with the increase in the demineralization time, that sample has find a significant increase in all the key temperatures. And these key temperatures are ignition, peak, and burnout temperature. And along with that, conversion efficiency was also improved. Well, this is actually a DDG analysis of cotton stalk sample. It actually represents the thermal cracking. Thermal cracking represents the vibration when there is a release of the energy takes place for the practical purpose. And the sample which has gone through higher acidification has shown multiple thermal cracking stages within the sample, and due to which there is a more amount of energy has been released. And we have a DSC analysis of the demineralized samples, and in this sample 3-HTDEM has shown maximum phase shift from endothermic to exothermic, as it can facilitate higher amount of energy untapping for the practical purpose. On this we have proximate analysis, and in this the most important component, the fixed carbon as well as the volatile metal, was found to be increased with the demineralization. In this we have CHN analysis of demineralized cotton stalk, and we have found that gradually all the samples has shown a significant effect on the basis of demineralization, whether it's a raw sample, whether it's a half hour treated sample, or we have a 3-hour treatment time based sample. I hope this is visible. Yes. In this, we have analyzed the burning conditions for different samples on the basis of ignition temperature. As we know, ignition temperature is required to ignite the fuel, and it can be witnessed from the results of an extensive study that as we are approaching towards higher demineralization time, our burnout temperature, our ignition temperature is decreasing. And same is the case when we are approaching towards reactivity. We have also found a different trend of that. Now we are talking about the kinetic analysis, and this kinetic analysis basically presents the demineralization and the activations energy concept. Activation energy, as we know, is one of the most important energy when you are talking about the solid fuels, because this tells about that what amount of energy is required in order to ignite the fuel, in order to take the energy out of fuel. And as we can see that almost in every fuel, the activation energy was found to be decreasing with the increase in the reaction order. Now we have structural characterization. Structural characterization of cotton stock, as it has the same similar study of the sample preparation, but in this, what we have done the crystalline analysis with the help of XRD and the hydroxyl group analysis from the FTIR analysis. So this is our XRD analysis, and in this, what we have observed that our angle of refraction was found to be increased with demineralization, while our crystalline index percentage was also found to be increased, was also found to be improved as we are reducing the amorphous content. And this is the results of FTIR, and in this we can observe that peaks between 3500 to 3000 has the stretching vibration for the functional of alcoholic and phenolic derivatives of hydroxyl groups, and it's quite in a trend formation. It's quite trending. There is a trend present in this. And the last, we have done the performance evaluation of sustainable biomass conversion, and in this we have done the same procedure like we have prepared the biomass on the basis of demineralization, and then we have analyzed the samples on the basis of heating rates and flow rates. We have a multiple heating rates, we have a multiple flow rates, and then we have gone through an extensive TGA study that is based on pyrolysis and combustion, and through which we have done the testing of TGA analysis, GTG, ignition temperature, we have mean temperature, burnout temperature, and then we have reactivity and activation observations. Well, this is a very extensive scheme of thermogravimetric study of the biomass on the basis of heating rate and the flow rate. And in this,
what is the SI unit?
That as our temperature is increasing, and while keeping the flow rate constant, our conversion efficiency was found to be increasing in all the temperature zones. We have observed this thing. At the same time, higher heating rates result in a shorter reaction time in the same temperature range, necessitating a higher temperature for sample decomposition, which is the prime goal of the research. Then we have a differential thermogravimetric analysis of cotton stock under various heating rates and flow rates, and there is quite significant variation on the basis of heating rate and flow rate. So it's all from all the DDGs, and within the range of 400 to 800 degrees C, it was observed that sample has gone through well decomposition, and solution that was being used for the main purpose was completely utilized. Well, these are the graph of ignition temperature dynamics in biomass degradation, and what it represents that with the increase in the heating rate, we have an increase in the ignition temperature. Now, if we look towards in a downward manner, like with the increase in the flow rate, there is also a very slight increase in the ignition temperature. The maximum weight loss temperature profile, it's a temperature at which we have a maximum weight loss and a maximum amount of heat is being produced. These are the trends for maximum weight loss And this observation has shown that maximum weight loss temperatures increases with a higher flow and heating rates. Higher maximum weight loss values were observed with an increase in flow rate, indicating enhanced mixing between the fuel and the air within the combustion chamber. Now we have the burnout profile. The burnout profile represents the complete combustion, the complete burning of the temperature. And the burnout profile says that with the increase in the heating rate, we have a higher retardation time. We used to say that the sample has gone through burning, complete burning at higher temperature stages, which is actually justifying the mature burning of the sample and which is actually required. So with the increase in demineralization, with the increase in the heating rate, we are actually achieving higher burnout time. These are actually all the burning combinations that we have developed, and on the basis we have mean reactivity and peak temperature. Well, this is the activation energy values and different reaction order, and in this we have 20 degree C, 30 degree C and 40 degree C, and right now we have an reaction order, and in this we have the lowest value, and same is the case. Extensive study was done on the basis of reaction order 2 by 3, 1 by 2 and 1 by 3. After that we have the conclusion. Experimental focus. The study investigated the burning dynamics of demineralized cotton stalk sample in waste to energy systems through thermal and structure analysis. Structural refinement. The structural matrix of cotton stalk was analyzed to observe decomposition in modified burning streams, aiming for efficient integration of lignocellulosic conversion in biorefinery setups. Acidification effect. In acidification, particularly through HCl-based hydrolysis, has improved the proximate and ultimate components of cotton stalk, leading to practical usage improvements and higher energy content. Then we have activation energy, and the study has reported decrease in the activation energy with an increase in demineralization time, indicating easier combustion at lower temperatures without external heating. Then we have reactivity enhancement. Acidification has increased the reactivity of cotton stalk, suggesting efficient in conversion to other forms of energy. Environmental impact. The research has aligned with the Sustainable Development Goals 7, 12 and 13, contributing to waste, biorefinery systems and cleaner energy productions. Biomass utilization. Findings has demonstrated that potential of demineralization cotton stalks as a competitive substitute for fossil fuels, reducing reliance on significant fossil fuel sources. This study emphasized the need for an integrated approach to fuel production, combining regional energy sources and various WTE techniques for sustainable environmental practices. And this is our future recommendation: integration of AI and robotics, hybrid biorefinery models that is based on biomass as well as conventional fuels, and then we have enhancement in carbon sequestration techniques. Thank you. Thank you. Any questions?
Thank you, Dr. Tayyab, for your inspiring talk. Now, I would like to request Dr. Tahir to please join us on stage and present us winner to Dr. Tayyab. Our final invited speaker for this session is Dr. Bandara Filio, full professor of mechanical engineering at Prince Mohammed bin Fahd University. He received his PhD from the University of Sao Paulo, Brazil, and has been recognized among the top 2% of scientists worldwide by Stanford University for 5 consecutive years. To date, he has supervised 4 postdoctoral fellows, 16 PhD students, and 21 MSc students. In terms of publications over the last 10 years, he has published more than 80 journal papers in top journals. His research focuses on refrigeration system, heat pumps, nanofloods, and heat exchangers. With over 80 journal papers and numerous international awards, he is one of the foremost experts in his field. Please welcome Dr. Bandara Filio for his talk titled Experimental Result of Nanoflood in Thermal Systems.
Go here. Okay, are you seeing my screen?
Yes, Professor. Visible and audible.
Okay.
Please proceed.
Much. So it's a great pleasure to be here once more. I was invited to be a lecturer in 2020 when I have a conference in Lahore. Supposed to be in person, but due to the pandemic, I have to deliver the lecture in online. It's here the second time. I will never accept anymore because I need to go to Lahore because I have a good history. In 2015, I met my first Pakistani friend. He's a professor in Lahore, by the way, Professor Amjad. And now I met Dr. Farouk. He's working here in the Prince Mohammed bin Fahd as well. So I have a good relation with Pakistani, but I never been in Pakistan.
That's great.
Anyway.
That's great. Our pleasure to see you and meet you again.
Okay, let's make a deal. Anyway, so it's a pleasure. I talk about a topic that I work since maybe 2009. So I have a lot of experience in this nanofluids topic, but it's difficult to understand the physical mechanism involved and as well application. So we still have underdeveloped a lot of things to do. So talk about a little bit me. I came in, here in Saudi Arabia. I was working in Brazil since 2004 as an assistant professor, and then now I came to 1 year here in Saudi Arabia. So a little bit more close to Pakistani. So here is just to know where my university in Brazil. Here is a map, and you can see here is Pakistan, and then here is Brazil. It's around 14,000 kilometers, so it's 6 times more than the Saudi Arabia, just to have an idea. And here is more close Brazil. Here is the most known city in Brazil, Rio de Janeiro. Here is the most crowded city, São Paulo, 30 million people living there. And here is my city where the university I came from. So that's just to understand where I came from.
Sorry, Professor, your screen is still. Please share the slide. We can see only your screen, static screen.
Okay, let's try to share again. It's okay now?
Yes, yes. Please go for a full screen, then we will.
This now you are see my screen research.
Yes, yeah. Math, yes.
Okay. So any problem, just interrupt me because this I still need to talk. So anyway, so just to have an idea, what is nanofluid? Mainly, most of the people understand this, but most of them think that's nano because it's very small fluid. It's not a very small fluid, of course. It's like a colloidal dispersion. In general, nanoparticles from 1 to 100 nanometers, and you disperse them in a liquid, in a base fluid that we can call. It's not like this, you have a powder or coffee or sugar or something like that, you mix with water, and then this makes one a single fluid. Nanoparticles is a little bit more problem because you are mixture solid nanoparticles in a fluid, and then you have two-phase flow in this case. When you have two-phase, it's understandable that most of the particles is not stable, so we stay here in the bottom. Here is some kinds of potential application for nanofluids. So mainly I like to show this graph because here you have the application. So related to the heat transfer process, we have refrigeration that I work on that as well. Not disperse nanoparticles inside the refrigerant fluid, but the potential is applied to the oil, lubricant oil. So I will talk a little bit about this in previous, in the further slides. In electronics, to become to dissipate more heat, solar absorption. That I will talk about this. This is a solar absorption. Here you can see in the bottom. Nuclear reactors to improve the critical heat flux as well. I will not talk about this, but it's one of the applications. Inside the electrical transformers, you can see here, electrical transformers work with oil inside to cool down this electrical part inside. So if you not cool accordingly, they can burn out. So that's other problem. In case of application in medicine, cryosurgery and drug delivery to, for example, treat cancer, to don't damage too many cells, and you go directly to the point to destroy cancer cells. In about application in vehicles, we can apply in car radiators that we work a lot on this in Brazil. We can apply in brake fluids, engine oil, fuels as well. So just to have an example about some kind of nanofluids, this one here looks like a yellow, is like a nanodiamond dispersed in oil. And here is difficult to understand, but this is a gold nanoparticle. So it's a very fancy, that's why I put here. So we're talking about diamonds and gold. So most rare material and expensive as well. Here, how we prepare the nanofluids. This is a very important and very understandable, because how we can disperse the powder inside the base fluid. So we have some three process. In fact, we can use sonication, that this probe here comes into the fluid, and here you can see the start process. You can see some powders here in the top and the water here, and then they start to sonicate the ultrasound, and then they disperse the nanoparticles inside the fluid. We have this other one. This is an ultrasound bath. We can just connect the electricity, and then the ultrasound bath by ultrasound waves can disperse the fluid. And this is another technology that we use in our lab that's called high pressure homogenizer. Just to have an idea, this equipment they use for make yogurt. Okay, just to have an idea. So the pressure here is around 800 bar. So it's a huge pressure, and then you can disperse the nanoparticles inside the base fluid. So this is called two-step method. First step method is just disperse the nanoparticles evaporating directly in the base fluid. So it's more expensive, and you cannot produce a lot. This you can produce a lot. When you're talking about nanoparticles or nanofluids, the first step is you have to characterize, because you cannot do anything without characterization. So we have these equipments in our lab to characterize, first of all, this thermal conductivity, so to understand how much we can improve the thermal conductivity. I will explain a little bit later on. We have this viscosimeter that we can measure the viscosity. Of course, we have the microscopy to see the dispersion, of course, if the particles clusters or not, and the spectrophotometer that we use to analyze the stability along the way, you know. So that's a basic equipment that you need to characterize your nanofluid that after you make. And how difficult is modeling this kind of nanofluid. Here is an example about different shapes of nanofluids. Diamond nanofluids, you see the shapes are very similar to a sphere. And here's same thing, that's a metal nanoparticle, silver one, is shaped like a circular one. So this is made by carbon, this is made by a metal. And then here you see a multi-walled carbon nanotubes. So it's carbon nanotubes. So you see different shapes. It's like a hair, you know. And then you have a graphene. This is the latest technology. They are used too much. This because the surface area is much bigger than the other ones. But you know, I just want to show you how difficult it is to propose a single correlation, for example, for modeling this. How you can integrate this kind of shapes. This one is circular. This one is like a tube. This one is like a foil. No, it's like different shapes. So how you can combine this? So that's why nanofluid encourage many people to enter and try to understand more and try to modeling and try to propose good things in the scientific world. Here is some kinds of results. I will show you some good things. Of course, sometimes you work with nanofluids and you don't expect or you don't find good results. But as a friend of us, a retired professor as well, he mentioned, you are not stellar, so you don't sell nanofluids. So you are a researcher. So doesn't matter. The most important thing is to do your research and get very important and good results for show to the literature and the community. Here you can see the thermal conductive results according to the time, the temperature. So we conduct some experiments from 10 degrees up to 50. And then the blue one here is the base fluid. In this case, it's water plus ethylene glycol, mostly used in the car radiators, okay? And here is our experimental results. This dashed line here is curve obtained by correlation by the engineer equation solver. It's a software. And then you can see here the results. So as you can see, here is about concentration. The red one is lower concentration, average concentration, and the purple one here is the highest concentration. And you can reach, of course, here around average improvements of 90%. This nanoparticles is silver with 20 nanometer of diameter, basically. If you increase the diameter of the nanoparticle for 80, for example, you can sometimes increase the thermal conductivity increment, as you can see here.
Professor Bandara,
Yeah?
Professor Bandara, sorry to interrupt you. We can't see your presentation view. Please open your presentation view. We is just seeing your, yes. If you go, yes.
Let's see again.
Yeah.
Now it's okay?
Yeah. Please you on the slideshow. Then we have a full view of your presentation.
Are you seeing me now or not? I change slides.
Yeah. You change, yes, thermal conductivity. Yes, you are visible. If you go for a slideshow, then it will be a bigger screen for the audience.
Okay, the problem is I'm seeing that. So I stop again and then let me put again. I don't know what is happening.
Yeah.
That's as I said to you, you have to invite me to go personally, in person to Pakistan.
We will invite you in future personally, physical.
Okay. So are you seeing me now, the transition?
Yeah. Please proceed.
Okay, as I explained to you, here is the 20 nanoparticles, and you can see some kind of increment, and here is 80 nanometers diameter from silver nanoparticles. You have a little bit more increment. Then here you have a single wallet carbon nanotube. This is another very interesting with high thermal conductivity element based on carbon that we got a very impressive results here. For example, for 50 degrees, you have increments up to 40% just for the thermal conductivity. Of course, this is related to the concentration as well. Here we talk about viscosity, because one of the things that you want is improve the thermal conductivity. But the other hand, when you add some solid particles inside your fluid, you increase the viscosity as well. So that's why our group, since the beginning, we always decide to work with very low concentrations, because this is more feasible to apply in reality, in the real world, so that's the most important thing for industry, because they can apply this in some heat transfer process. So here is about the viscosity, as you can see here, very well correlated. And here is about the increments. For this kind of concentration, for silver nanoparticles, we got just maximum 2.5% of increment. That's a very good, because this reflects direct to the pumping power. Okay, so, and you can see this, you cannot take too much pumping power. Talking a little bit about stability, this is a results from our equipment that I showed you before, the spectrophotometer, and then they measure the absorbance of the fluid. So after 30 days here, for example, these multi-wallet carbon nanotubes just reduce 10% from the stability. So this kind of nanofluids show very, very encouraging results, because you, from 30 days, like static, stopped without circulation, you just reduce 10% for the concentration. That means a lot. That means a very encouraging results to application. Talk a little bit about more now about facilities, about what we have in our lab. Okay, first of all, we have to understand about the basics. Basics, I mean heat transfer. So how we can improve the heat transfer in using nanofluid. So we built this facility, is a circular facility to circulate the nanofluids inside the tube. And here we measure the wall temperature, and we measure the fluid temperature inside as well. And we apply a heat flux in the wall. So with this, you can calculate the heat transfer coefficient directly. So we can test base fluid, water, ethylene glycol, oil, thermal oil, for example. So we test this a lot, and we can compare these results. Here is some very interesting results. I call this figure of merit. What does it mean? This is the heat transfer coefficient obtained by nanofluid over related to the base fluid. So up in this quadrant here, higher than 1, that means the heat transfer of nanofluid is better than the nanofluid that we expected. And this quadrant, this X here, is like a pumping power of nanofluid over the base fluid. So all of the results was like in this quadrant. And the best results was like obtained by this carbon nanotubes here. So concentration 0.24. Are you following my slides?
Yes, Professor. Please, and
Okay.
next.
Perfect. Next one is about our next experimental facility. We built a wind tunnel to test car radiators. This is motivated by a company, Fiat, in Brazil. Is a huge company there. And we made a joint project and to test the nanofluids inside the car radiators. And of course, we can test as well some heat exchangers in any size. So the car radiator here, what's the advantage? When they cool down the engine, if you improve the thermal performance, you can reject more heat. So this you can make the car running better and avoid improve performance, in fact. So here is our wind tunnel that we built in the lab. So very well instrumented. Here is the circulating, we put the radiator here inside the wind tunnel. And here is the facility to circulate the nanofluid inside. We measure here, you can see the mass flow meter that we measure here, the micro pump to avoid any contact with the nozzles. Okay, very well instrumented, by the way. Here are some results using graphene in this case. Okay, 50% of volume, 50% of water glycol, and 50% of ethylene. Here is the heat transfer. So as you can see here, the heat transfer increase by a average amount, and that's very, very encouraging results. And by the way, we were the only group in the world that could test car radiators over 100 degrees. So we reach up to 110 degrees. That's a very tough task because the nanofluid didn't make any more stable when you get this temperature. And we were the only one that we can get. This is one of our latest publication, very well cited in Applied Thermal Engineering. Here is another very interesting facility that we have is nanofluids in solar absorption. So that's a very encouraging result. This is gold nanoparticles, gold nanofluids, and the results show a very interesting thing. So here using, for example, carbon nanotubes, we can improve the water temperature from 30 for base fluid up to 70. So you see the amount of energy that you can absorb on this. And here is about the refrigeration system. As I told you, it's not feasible to use in the refrigerant fluid. Yes, and we used to in the lubricant oil. So we apply nanoparticles inside the lubricant oil that we got a very interesting results as well. Here is a nanodiamond, okay, and how it works. We can have different works to explain the improvement of performance of nanoparticles. So we have a bearing effect, we have protective film, we have polishing, that's one of the things. All of these mechanisms, we can improve the performance by reducing reduce friction inside the compressor. So that's one of the reasons to improve the performance, the COP of the system. Here's just I have analysis. This is efficiency, COP, coefficient of performance of nanolubricant operating with the refrigerant R410A. That's most used for refrigerant for air conditioning system. And here is the result. So we have a lot of improvements and using nanolubricants. That's one very encouraging results for the refrigerant industry. And the last application, our last, by the way, our last publication, this maybe 20, 30 days ago, is about using nanofluids inside the microchannel. So we built this facility here just to understand or just to study what is the behavior of nanofluids inside the multi-micro channel here. This channels is around 400 micrometers. Just to have an idea, this distance here is 1.3 centimeters, 13 millimeters, okay? So what the results that we get here, coefficient, that's very important. And by the way, we use here very ultra low concentration. That means 0.005% of concentration. So that's a very, very interesting because you don't aggregate too much value for the industry. But by the way, you have a heat transfer improvement. So finalize my talk today. I'd like to show this slide. This slide is very interesting for me because show if you try to do your research alone and compete with other research, sometimes you will die because you cannot eat. Anyway, and if you go agreement, if you cooperate, everyone will be happy and everyone will grow and understand more what is going on. Thank you very much. And this, I finalize my present.
Thank you, Professor Bandara. Thank you for engaging us. Our wonderful presentation of nanofluids and thermal system. Your talk provided a valuable perspectives on the application of nanotechnology for improving thermal performance. Thank you. We will see you again, inshallah, in presence. Thank you.
Inshallah.
Thank you.
In case conference.